All right, section 11 point vectors, page 2. In this example problem 3, we're asked to determine component form of a vector. So we're going to let vector A be the vector of length 17 that when drawn in standard position makes an angle of 123 degrees with the positive x-axis. Write A in component form, round approximations to the nearest thousandth. So let's go ahead and here and try and sketch out this vector. You know my opinion, a picture is worth 1,000 words, so I'm going to try and draw this vector. It has a magnitude of 17 and an angle of 123 when drawn in standard position. So it's going to be up here somewhere in quadrant 2, and it has a length of 17, and the angle that it makes with the positive x-axis is 123 degrees. Now I'm drawing you that picture just because I think it's important to have an understanding of what the vector looks like, but determining its component form is really pretty easy. So vector A in component form will be equal to the magnitude of vector A times cosine theta comma sine theta. So let's go ahead and plug in what we know. The magnitude of vector A is given to us as 17, and we know the angle is 123 degrees. And I'm going to go ahead and crank that out with my calculator, and I get the following, rounded to the nearest thousandth, negative 9.259 and 14.257. Folks, make sure you're in the right angle mode. This was needed to be in degree mode to determine the cosine and sine of each of these two angles of 123 degrees. Okay, so let's just take a stock of this answer and make sure it makes sense. If my horizontal component is negative and my vertical component is positive, I better end up in quadrant 2, which certainly looks like my picture. So that's good. I'm now ready to move on to part B. Part B says consider the vector A from the previous problem and a new vector B which has a length of 20 and makes an angle of 320 degrees with the positive x-axis when drawn in standard position. Determine the length of the vector A V, which is vector A plus vector B, and the angle theta degrees that V makes with the positive x-axis. Round approximations to the nearest thousandth. Okay, so this one a little trickier than the previous problem. I'm going to go ahead and try to sketch a picture out here. This is tougher to, when I'm drawing two vectors that are added together, a little bit tougher to draw the picture. Okay, so what I've done here to try and sketch this problem out for you is I've copied my vector A from the previous problem. I've shrunk down my angle and my magnitude just so I have room to draw some other stuff on there. And what I'm going to do now is draw the vector B, which has a length of 20 and an angle of 320 degrees with the positive x-axis. So that's going to look something approximately like this. It's going to be a little bit longer than the previous vector, and it's going to be 320 degrees rotated around from the origin, which means that this angle right here, if I extend the x-axis here a little bit so we can see this, this is going to be 40 degrees. And the reason why that's 40 is because 320 plus 40 gives us 360. Okay, and this is vector B. And remember that this previous vector is vector A. So if I've drawn these to scale, and I remember that when I add two vectors, the tail of the first vector to the tip of the second is my new vector. So my new vector should look something like this, assuming that I've got all of this drawn to scale approximately correct. That should be my new vector V. And let's go ahead and do the work to show what the component form of that vector is. First thing I'm going to do is say that vector v is going to be equal to vector a, which is got a horizontal component of 17 times the cosine of 123. And then I have to add to it the horizontal component of vector b, which will be 20 times the cosine of 320 degrees. So that's the sum of the two horizontal components. Now I have to add to that the vertical components. For vector A, that's 17 times the sine of 123 degrees. And for vector B, that's 20 times the sine of 320 degrees. When you add these two values together, you are going to get the component form of vector V rounded to the nearest thousandth as 6.062, comma 1.402. Now let's ask ourselves, does that answer pass the sniff test? Well, if I look down here at vector V, it looks like it's going to be up in quadrant 1 somewhere. It looks like the horizontal component is going to be larger than the vertical component, which makes sense with what I have. And again, this is only approximately drawn to scale here, so this is at least, I believe, that my picture matches my answer. But we're not quite done with this because we were asked for some additional information. We have to determine the length of the vector and the angle that it makes with the positive x-axis. Okay, so the length of vector v will be 6.062 squared plus 1.402 squared, and then I have to take the square root of that. And let's go ahead and see what that is rounded to the nearest thousand. Folks, that gives me a magnitude of 6.222 rounded to the nearest thousandth. And folks, one of the things I realized I just did on this problem is I found the component form first, which is a good idea to do, but I'm using rounded values here. We were only asked to find the magnitude of V and the angle that it makes with the positive x-axis. So I'm using rounded values in this calculation. If that rounding causes more rounding error than is acceptable in WebAssign, you may have to keep more than just 3 decimals in each the x and y component of the vector. Now for the angle, this is in quadrant 1, so it's pretty easy. It's going to be the inverse tangent of the y component divided by the x component. So theta equals the inverse tangent of 1.402 divided by 6.062, and that gives us an angle in degrees of 13.022 degrees. And folks, really, to measure something to the nearest thousandth of a degree is kind of ridiculous. I think the most I'll ask you for on a test is the 10th or 100th place. To be honest, I'm not exactly sure what WebAssign asks for. Okay, so for the vector v, we have a magnitude of 6.222 and a direction of 13.022 degrees. All right, let's move on to example 4. Example 4 is a tricky one because this is really a physics problem. So I mentioned that there are a lot of applications of vectors in physics and engineering, and here's your first example of that. So I'll let you go ahead and read the problem. But really what we're asked to do here is find out whether or not the tension in this wire and this wire it exceeds the allowable tension of 200 pounds. So it says that the wire will snap if the tension is above 200 pounds and the weight hanging on the weight hanging down here is 220 pounds. So let's see what happens here. I'm going to go ahead and annotate the figure and teach you a little physics in the process. So this point right here represents the person hanging off the 2 ropes. That happens to be me, and at one time I weigh 220 pounds. What I'm going to do now is I'm going to call this tension number 1, and I'm going to call this tension number 2. Tension number 2 has both a horizontal and vertical component. Okay, we can think of the horizontal component like that, which is going to be T2 times the cosine of 18 degrees. And it has a vertical component right there, which is going to be T2 times the sine of 18. Let's look at T1. Same type of situation over here, except the horizontal tension is going to go this way. So that's T1 times the cosine of 63 degrees. Better move that off of the other label in the problem. And the vertical component there, which is going to be T1 times the sine of 63 degrees. Okay, now we're ready to talk about the physics of the problem. First thing we're going to do is an analysis of horizontal forces. And this is the part of the physics you need to know. We're making an assumption here that nothing's moving. Everything is static. Once I jump off the bridge and I'm hanging there, nothing's moving. So the horizontal forces must balance. And if the horizontal forces are balancing, that means the following is true. This force right here must equal this force. They're in opposite directions. They must equal each other. If they're not equal to each other, then there will be motion. So that means I have T1 times the cosine of 63 degrees has to equal T2 times the cosine of 18 degrees. And from this point, what I'm going to do is I'm going to solve this thing for T2. T2 equals T1 times the cosine of 63 degrees divided by the cosine of 18 degrees. One thing I am going to do in this problem is I'm going to convert everything to decimals at this point, just because I think it might be a little easier for you guys to follow. So I can now say that T2 equals cosine 63 divided by cosine of 18 gives me the following: 0.4774. I'm rounding that to the nearest 10,000th place. And 0.4774 times T1. Okay. If you look at my notes that I post online, you'll see that I keep the entire problem symbolic until the very end, at which point I calculate what each of the tensions are. So, all right, we have this relationship here that just tells us the relative, the relationship between T1 and T2, but that's not really what I need to know. I need to know exactly what T1 and T2 are, because if they exceed 200 pounds, then the line snaps and I fall, and that's very unfortunate. So what I have to do now is I have to do an analysis of the vertical forces. And they too must balance, otherwise things will be moving. And because they balance, the following must be true. Okay, so let's take a look back at our picture now. The vertical components of the forces, this vertical component here, and then this vertical component here, must be the same. Those two added together must equal 220. If they're more than 200, if they're less than 220, then we're going to have an issue. There will be some motion involved. So the sum of this force vertical component and this one must be equal to 220. So let's go ahead and write an equation showing that the two vertical components of the tension in the wires must equal 220. It's going to look like this. We're going to have T1 times the sine of 63 degrees plus T2 times the sine of 18 degrees equals 220. Well, unfortunately, this is one equation with two unknowns, T1 and T2. So if we don't have something that we can substitute in here for one of the unknowns, we'd be stuck. Fortunately, we do have something. We have this relationship right here. From the previous part of the problem, when we analyzed the horizontal forces, we have T2 equals 0.4774 times T1. So I'm going to go ahead and substitute that in right now. This is going to give me T1 times the sine of 63 degrees plus T2, which is 0.4774 times T1 times the sine of 18 degrees, and that has to equal 220 pounds. Now what I'm going to do now is I'm going to convert this to a decimal and then this to a decimal, and notice how these are like terms. They both have T1 in them, and that's going to result in the following. So the sine of 63 is about 0.8910 times T1 plus 0.4774 times T1 times the sine of 18, which is about 0.3090. That still equals 220. Go ahead and combine all these like terms. I get the following: 1.0385 times T1 equals 220. And this previous step might be easier to see what I was doing if I had some parentheses in there. So it's sum of these two terms is 1.0385 times T1. I divide both sides by 1.0385 and we get T1 equals 211.84 pounds. And folks, that is a problem. Unfortunately, T1 is greater than 200 pounds, so the lines will snap. And that means I better have a plan B, otherwise I'm falling all the way off the bridge. I guess another solution could be the following. Perhaps Mr. Vass should shed a few lbs. Okay, folks, that's it for this problem. One thing I do want to remind you about here is we just did a physics problem, and we did a force analysis problem where it's called a static force analysis, static meaning nothing's moving. So the sum of the forces in the x direction and the sum of the forces in the y direction must balance. That's what enabled us to solve for a relationship between T1 and T2, and then eventually solve for T1, showing that it was greater than 200 pounds and will snap that cable. Okay, folks, that's a vector application, and go on to the next video for some more vector work.